Okay. So last time we started to construct normalizations, and maybe let me recall what is called normalization. So we have an irreducible algebraic variety y, and its normalization x, or sometimes y tilde, is another variety projecting onto y, such that first of all, they are generically isomorphic. That is, they have the same field of rational functions. Sorry. And also x is normal. That is, all the local rings O x are integrally closed. Okay, and more generally, we introduce the notion of normalization in a given finite field extension, L over the field.
В смысле integrally?
Integrally closed. Well, it's such a notion of basic algebra that all the algebraic equations with leading coefficient 1 that have solutions in the field of fractions, they do have solutions in the ring itself.
Спасибо.
Yeah? Okay. There is a finite extension of the field of rational functions, and then x is a normalization of y in this field extension if, again, x is normal, but now the field of rational functions on x is this field extension L. Okay, and now we're going to construct those normalization. And as I said last time, this is the relative spectrum of some coherent sheaf of algebras. Over y. And it is defined as a subsheaf in this big sheaf, constant and quasi-coherent sheaf L tilde. Of y modules. Namely, for an open subset V in Y, we set A over V equals the intersection over all points in this open set of integral closures of the local rings O V in L. Okay, integral closures of these rings in the ambient field L. Okay, this is the construction, and we only have to check that it works as stated. So, well, I don't know. Let's call it proof. And what do we have to check? The following thing. First of all, that this is A is coherent. It's clearly sheaf of algebras, and there's a local question. So we may assume that our Y is affine. And in fact, you see that all the other questions are local as well. So you for everything here, you can assume that Y is affine, and we do assume that Y is affine. And then what do we have to check? So first of all, we have to check that the sections of this sheaf of algebras is the integral closure of the ring of functions on Y in our field L. Second, we have to check that this ring of sections is a finite ring, finite module over the ring of functions on Y, or finite type module. Then we have to check that it commutes with localization df is the localization with respect to a regular function f. And finally, we have to check that the spectrum of A of Y is normal, or in other words, A of Y is integrally closed, and its field of fractions is our field L. Okay, so now let's go to the next page and check those properties. So, well, the first property we'll check is that our sections on the global sections A of Y is the integral closure. Okay, so how do we do this? Let's denote the integral closure of the ring of functions on Y in L by something like A, and then the key point is that the key observation is that the integral closure commutes with localization. Okay, and from this, it follows that the sections of our global sections of our ring is the intersection over all points in our variety Y of this ring localized in V. Okay, but now this this thing by definition is the global sections of localization of this A. Okay, if you still remember from our November days when we studied quasi-coherent sheaves, global sections and localization, then by definition, the global sections of localizations are just well, it's just the intersection of all localizations at all the points. Okay, but now this is nothing but A. Okay, and so we proved our claim that the global sections of our sheaf of rings is the integral closure in our field. Okay, so we proved 1. Now, what is 2? 2 says that the global sections is a finite model over the ring of functions, and this is immediate. Yeah, that the integral closure of any ring in a finite field extension is always a finite module over this ring. There's some basic algebra result that is assumed to be known to everybody. Now, what is the next point? The next point is that it commutes with localizations. But we just mentioned that it does commute with localization. Again, integral closure commutes with localization. And finally, the last point is that the spectrum of this ring of the sheaf of rings is normal with the correct field of fractions. And once again, it follows by the same key observation that the integral closure commutes with localization. So we know that we already know that the global sections are integrally closed in L, and again by commuting with localizations, it means that for any point x that is the spectrum of A of y, the localization at the corresponding maximal ideal, this is the same as the local field, the local ring at this point is integrally closed in our ambient field L. Okay, so everything is proved, and the key point was one last time that the integral closure commutes with localization. We used it everywhere. Okay, and then maybe one last claim is that for an irreducible variety, the set of normal points those where the local ring is integrally closed in the field of fractions, field of rational functions on Y. So this set of normal points is open and dense in Y, and the proof is immediate because we do have this normalization. It's the normalization. So in the field of rational functions on Y, we do not extend this field, and we know that it is generically an isomorphism, just by rational isomorphism. Okay. And then it means that we have the direct image sheaf of this normalization, and this sheaf is a sheaf of finite modules over the structure sheaf of Y, and also generically it's isomorphic to the structure sheaf of Y. Okay. Okay. So we have an embedding of Y into this direct image. And this embedding is generically an isomorphism. And how to say, let's consider the closed subset. X in Y. This X is the support of the quotient sheaf. Modulo of Y itself. Okay. And the complement Y minus X is the desired open set. Okay, so for any point in U, the local ring at this point is already integrally closed. Okay. So the properties of being a smooth point is open. We proved that the smooth locus is open dense, and the normal locus is also open dense, but they're in general they are different. So we have Y smooth is contained in Y normal is contained in Y. And in general, they may be all different. For example, as I told last time, if you consider a two-dimensional quadratic cone, then it is not smooth at the origin, at the vertex, but it is normal everywhere. But for the curves, as I also said last time, and I will hopefully say it in half an hour once again, for the curves, normality is equivalent to smoothness. Okay, and in fact, the as we'll see next time, there is a construction of curves that is very similar to this construction of normalization we just studied 10 minutes ago. I mean, this intersection of local rings is a very useful construction. Okay, and now let's prove another very useful theorem due to Bertini. And it is about projective varieties. So we start with an irreducible projective variety and smooth. Okay, and we are going to consider its hyperplane sections. So H in Pn will be a hyperplane. And we can take the intersection. Okay, so now this theorem states that for general hyperplane, this intersection is smooth. And in fact, if x was not a curve, then this intersection is irreducible, equivalently connected, because you know that a point at intersection of two irreducible components cannot be smooth. So since we know that it's smooth, then its irreducibility is equivalent to its connectedness. So the claim is that the intersection is also connected, but somehow at the present moment we cannot prove this connectedness property. It requires some cohomology computation. So we will only do this maybe in February, but at least we'll prove that for general hyperplane, the corresponding hyperplane section is smooth. Well, I'm not sure if I can draw it, but maybe if you imagine your x just a circle, then you see that the typical intersection consists of just 2 points. It's disconnected because x is one-dimensional, but at least smooth. But there are intersections like this, and here you have a tangent point, so it will have multiplicity 2. And well, we discussed this with Ivan Matorin in the end of last semester. I mean, this point is supposed to be smooth or not. So scheme theoretically it's not smooth, but if you take it as sorry, what did I do? Oh, sorry. Yeah. So if you somehow forcefully kill the nilpotence, then it's just one point and it's still smooth. But maybe I should draw some. No, I think I'm not able to draw a higher dimensional picture, but still you can probably believe me that there will be some non-smooth sections. But generically, the sections will be smooth. That's the content of this theory. And now let's prove it. Well, all the possible hyperplanes H in our space form the dual projective space P dual. So if our projective space was projectivization of some vector space, then the dual project space is the projectivization of the dual vector space. Okay. And so this is the space of parameters of hyperplane sections, and we want to find an open subset in this dual project space, such that for any hyperplane there, the section will be smooth. So we will find an open U inside the dual project space, such that for any point in this open subset, the intersection of the corresponding hyperplane with X is smooth. Okay, and to this end, we will consider the universal family of hyperplanes. Well, maybe let me call it H calligraphic inside the product P times P dual, or maybe it's also called the incidence variety. So this is the set of points X in a P and H in P dual, such that the pairing H and X is 0. It's well defined, right? So X is a point of the ambient vector space defined up to scaling, and the same for H, but this condition is homogeneous, so it's well defined. Or in other words, that's a point and the hyperplane such that the point lies inside the hyperplane. So equivalently, X lies in the corresponding hyperplane.
Определение этого спаривания. Или я прослушал, что означает скобочки эти?
These brackets mean that the corresponding vectors in V, there is a pairing between V and V dual. So you lift your X to any vector in this line, and your H to any vector in that line, and those two lines must be orthogonal. Okay.
Спасибо.
I cannot say that the pairing is equal to some non-zero number, but if I say that it's 0, then it's well defined. Okay.
Спасибо.
It doesn't depend on scaling or rescaling this vector. Okay. So so what do I do now? Inside this H, I now consider subvariety Z given by the following conditions. So first, I require that X actually lies in my subvariety. Okay, and second, I require that the corresponding section acquires singularity at X. That is, I require that the differential that is tangent to X, so to say, the differential of this form, the sum of H I X I, okay, this pairing is 0. So it means that the hyperplane H sub H is tangent to X at the point X. So the intersection H with X is singular at point X. Okay. So then we will have projections from Z to our original X, well, inside the original project space, and also to the dual projective space. Let's call it P and Q. Our aim is to prove that Z is so small that it cannot cover the dual project space under this projection Q. So we will prove that the dimension of Z is less than n, and hence Q of Z is well, closed and strictly smaller than P dual. Okay, but again, since this morphism is projective, this is necessarily closed. So the complement will be open and non-empty, and that's what we want to prove. Okay, so we only have to compute the dimension of Z and prove that it's less than n. Now, let's assume that our original X is not the whole of projective space. Otherwise, there is nothing to prove. And so the dimension of X is smaller than n. Okay, and now it remains to prove, or suffices to prove, that for any point in X, the dimension of its fiber, this P projection from Z to X, is less than n minus dimension of x minus 1. Okay, because then by the general dimension theory, the dimension of z will be at most this plus dimension of x, that is n minus 1. Okay, so we only have to estimate the dimension of fiber. Now let's look what is the fiber. The fiber over x is the set of H such that, first of all, they are orthogonal. So the sum of H I X I is 0. And second, the differential at this point of the sum Hi Xi is also 0. So the first condition is that the point x does lie in this hyperplane. The second condition is that this hyperplane is tangent to the ambient variety at this point. Okay. But now you see locally, so the whole thing happens in the projective space, but this question is already local, and we may assume that everything is in the affine space, say in some affine chart containing this small x point. And then
Извините, а где мы p ввели? Вот это p это что?
P is the projection from z to x. You see,
это p.
From z to the dual project space and to the original project space, right? And P is projection to the original.
Просто вы греческое обозначили внизу там свой.
Oops, sorry. Yeah. It was not. Sorry. It's not pi. It's just P. Sorry. Hopefully nowhere else. Sorry. Okay. So there are two projections like this, and altogether, this lies. This is just a number, and it lies in so to say O x modulo its maximal ideal, and this lies in the maximal ideal by definition modulo its square. Okay.
Разве из пункта А не следует сразу пункт Б, ведь если вы там число продифференцировать, то 0 получится, так? В чем разница?
Well, by the same reasoning, df is always 0 because f assumes numerical values, and when you differentiate numbers, you get 0. So it's not very convincing argument. And now here you have dimension. So x was a smooth point. So the dimension of this cotangent space is the dimension of x, since x is smooth. Okay, and since in this local chart the functions are just linear, you see, it's a bilinear function. It's hi times xi, and then you add up. So in h it's a linear function, and in x it's a linear function, and this way certainly you the map from all functions to this maximal ideal modulo its square is certainly surjective. You can find an appropriate linear function with a given differential. So I mean that you do get exactly dim x conditions, equations. And the first condition is also linear and independent from those, independent of the previous of B relations. Okay, so altogether you get d max plus 1 independent, well, linearly independent equations. Maybe I should say linearly dependent linear equations on H. So in other words, these relations give a surjective map, say from V dual to O x modulo the square of the maximal ideal. The point is that it's surjective. And the dimension here is dim x plus 1, right? Fine. So we found dim x plus 1 linearly independent linear equations, and hence dimension of fiber is at most what was it? Dimension. What do you want? We wanted n minus dimension x minus 1. Sorry, in fact, here it was not a strict equality, like this, and that's what we proved. N minus dimension x minus 1. Okay, great, and we proved this Bertini theorem, and it's a very important theorem. We'll use it many times in our next slide, or in spring. So, okay, but now let's move to the next very big and very important topic, namely the curves. So already today we will see that the curves are simpler, not just because they have dimension 1, but in many other respects they're simpler than general algebraic varieties, and many things can be proved very explicitly and clearly for curves, and then sometimes generalized to higher dimension. So we'll start with some general lemma that we'll use today later on. So we start with an irreducible separable variety x, and we have two points, x1, x2 there, and suppose that we know for some reason that their local rings are embedded. The local ring of the first point is embedded into the local ring of the second point. And in what sense? Well, anyway, all the local rings they live in the field of fraction. Okay, and well, it's a strange assumption, but suppose it happens. And not only this, but also the maximal ideals are also embedded. Okay, but if such a strange thing happens, then definitely the points coincide. Okay, and this lemma will be a basis of our construction of curves. Namely, I somehow I mentioned this construction many times. What I mean is that the isomorphism classes of smooth curves, say smooth projective curves, are the same as isomorphism classes of field extensions of our base field of transcendence degree 1. Okay, so there's a natural bijection between smooth projective curves and fields of transcendence degree 1 over our basic field. We'll prove this next time, and today only a preparational lemma. Okay, so let's prove this silly lemma. So let's take an open fine neighborhood of x1. And let's choose generating functions, say f1 and so on, fn over regular functions on this neighborhood. And well, we know that they are regular at x1, so they lie in the local ring of x1, and by our stupid assumption, they also lie in the local ring of x2, so they are regular at x2. Okay, and let's take a neighborhood v2 containing x2, where all these f1 and so on, fn, really are regular. Okay, and then by construction, the regular functions on v1 are contained in regular functions on v2, right? Because the regular functions on v1, by assumption, are generated by f1 and so on, fn. Okay, now the intersection v1 intersected v2 is the spectrum of their product, regular functions on v1 times regular functions on v2. But we know that regular functions on v1 are contained in regular functions on v2, and so this is just the spectrum of regular functions on, v2.
Что такая окрестность найдется в V2, где вот эти f1 и fn регулярные?
Because by our stupid assumption, any function regular at x1 is regular at x2, and we need only finitely many f1 through fn to generate the function of this first neighborhood v1, and for finitely many functions, we can find one common neighborhood of x2 where they are all regular. Okay.
Спасибо.
Okay. So we proved that the intersection of V1 and V2 is contained in V2, and it means that so it's not contained. It's equal to V2, and hence we know that V2 is contained in V1. Okay, so in particular, we know that both x1 and x2 lie in this V1. Okay, and now we're almost done. So if we have a function regular on V1 such that f of x1 is 0, then f of x2 is also 0, right? Because of our stupid assumption that the maximal ideal of x1 is contained in the maximal ideal of x2. Fine. It means that x2. Sorry. X2 lies in the closure of x1. Okay, but it only can happen if x2 equals x1. Very stupid lemma and very stupid.
Зачем брать замыкание точки? Разве точка не замкнута?
Well, that's the point. Once again, I argue that any function vanishing at x1 vanishes at x2 as well. But by definition, this means that x2 lies in the Zariski closure of x1. But as you say, the Zariski closure of a point x1 is just the same point x1, nothing else. So x2 must be equal to x1. Okay?
Когда такое может не происходить? Что замыкание точки не совпадает с самой точкой?
No, in our theory so far, all the points are closed points, and their closures are just the points themselves. Okay, so not in this life. Okay, so now we can prove something substantial, namely that let's take a curve, and it's a irreducible curve, and a point in this curve, and then the following conditions are equivalent. First, that C is a smooth point. Second, that this local ring is integrally closed. This is what I promised many times, right? That for curves, the smoothness and normality are equivalent. And finally, that this local ring is a DVR, discrete valuation ring, meaning that there is a uniformizer pi in the maximal ideal of this point in this ring, and any well, and sorry, that any element of this ring, f is of the form some power of this uniformizer times some unit. So n is the positive integer and u is a unit. Okay. So let's prove this. First of all, from C, we can deduce B immediately. Because a DVR is a unique factorization domain, and for unique factorization domain, the integral it's integrally closed, and it's easy and well known. Okay, now let's prove that A implies C. So we know that it's a smooth point, and we want to prove that it's DVR. The basic thing is that the maximal ideal modulo squared is one-dimensional. Okay. Well, any two elements of this quotient differ by a scalar. Okay, and we just take any element. Sorry. We'll take any element pi in maximal ideal, but not in its square, and then the maximal ideal is generated by this uniformizer, say by Nakayama lemma, if you wish, and now let's take any element in the local ring, and we want to prove that it satisfies this DVR condition, that is, it's proportional to some power of the uniformizer. Okay, so well, what can happen if it's not proportional to some power of the uniformizer? Then it is infinitely divisible by the uniformizer. If f is never of the form pi to some power times a unit, then is infinitely divisible by pi. And say we can set fn equals f over pi to the power n. It's always divisible, and hence we have an increasing sequence of ideals. F that is, well, f0 is contained in f1, and so on. Now by the Noetherian property, of our ring, this must stabilize. So at some point, this ideal is the same as the next one. And it means that when you divide by pi to the power n, it is proportional to f divided by pi to the power n plus 1 for some element in our ring. Okay. And this implies that 1 equals a times pi. And this is impossible because pi is not invertible. Okay. So we proved that A implies C.
Сейчас,
Okay.
почему
Yes.
Почему f не может просто не делиться на i?
Because our maximal ideal, remember, let's go back. The maximal ideal was generated by pi, right? So if f is not divisible by pi, then f is out of this maximal ideal, and then it is invertible, right? It's a local ring, so everything that is out of the maximal ideal is invertible, right?
А мы разрешаем n равно нулю быть.
Oh yes, certainly, yes, absolutely.
Хорошо, спасибо.
Welcome. Okay, so it remains to prove that B implies A. Okay, so we assume that where we're here that our local ring is integrally closed, and we want to prove that it is smooth. Okay, so again, the local question. So we can assume that C is an affine curve. And f a regular function that cuts out our point, and moreover, we can, if it vanishes somewhere else, we can just remove those other zeros. So our curve is still affine, but a little bit smaller. So maybe say C is exactly the only zero of this function f. Okay, then by the Nullstellensatz, we know that some power of our maximal ideal is contained in the principal ideal generated by this function. And now there's a strange claim we're going to prove, namely that either the maximal ideal is a principal ideal, or else we can somehow descend. So its smaller power is also contained in the principal ideal generated by f. Okay, so from this claim, well, the maximal ideal has to be a principal ideal. Otherwise, we do this infinite descent and we end up with the maximal ideal to the power 0, that is just the local ring itself, is contained in F. And there's nonsense. So the maximal ideal must be principal. And it means that the quotient modulo square has dimension 1, and means that C is smooth. Okay, so that's what I wanted to prove. So it remains to prove the claim. Well, let's take an element of the smaller power, the y in the n minus first power. Then we know that when we multiply this element by the maximal ideal, it gets into nth power that is contained in F times the local ring. And it means that the ratio y over F times the maximal ideal lies in the local ring. And now there are two possibilities. So either y over F times the maximal ideal is the whole local ring, or the second possibility, this ratio lies in the maximal ideal. Okay, because this is the local ring, and there's nothing else. There's a unique maximal ideal. Okay, so so if we have the first possibility, y over F times the maximal ideal is the whole local ring. If this is so, then the maximal ideal, is F over y times the local ring is the principal ideal. That's what I want to prove. So it's good. And otherwise, we have the second possibility. The second possibility is that this ratio times maximal ideal lies in the maximal ideal. For all our choices of y. And then this multiplication, so multiplication by y over f is an endomorphism of a finite O module, this maximal ideal, and hence this y over f satisfies an equation with leading coefficient 1, namely by Kelly-Hamilton theorem. Maybe you remember it from some of the first home assignments. But now we assumed that our local ring was integrally closed. Then it implies that y over f lies in this ring. Okay, and again, this is true for any y. Okay, and this implies that the maximal ideal to the previous power lies in the principal ideal generated by f. Okay, and there we are. That's what I want to prove. Okay, so it was an important point. Once again, we proved that for curves, the smoothness is equivalent to normality. Okay, and also to the property of being of any local ring being a discrete valuation ring. Okay. Okay. Well, maybe let me say the most stupid example. This cuspidal curve given by x squared equals y cubed inside A2. And so what is bad about this point? So why is this local ring 0.0 not DVR?
It is not integral.
Pardon me?
It is not integral.
It is not integral. Yeah,
Integral
but maybe that I assume this is known. But why it's not DVR? Why is it not DVR?
Like one-dimensional Noetherian integral cross string is DVR, but it is not DVR. So it is not integral cross. So like this is not DVR.
Yeah. So well, so neither y nor x will work for the uniformizer phi. Okay, because of this relation, x squared equals y cubed. Okay. So now let's prove one last thing. Since we have 5 minutes. Again, we'll use it next time, but today we only make some preparation. So suppose we have a morphism between two curves. f from C to D. These are curves. And the base curve is smooth. But the morphism is birational. So they have the same fields of rational functions. And then I claim that necessarily the image of F is open. And this F is just an open embedding from C, an isomorphism, onto F of C inside D. Okay. So we discussed the normalization. Yeah, and normalizations work from a smooth curve to another non-normal, non-smooth curve. But you cannot have a morphism from non-smooth curve to a smooth curve. Okay, that's the point of this proposition. You can have resolution of singularities, normalization from smooth to non-smooth, but not in the opposite direction. Okay, so let's prove this. So first of all, we know that it's birational. There is an isomorphism between open subsets of our curves. Okay. So in particular, the image does contain an open subset U in the base in our smooth curve, and the complement is finite because we are in curves, right? D without of C is finite, and hence closed. And we may replace D by this image and assume that F is surjective. And then we have to prove that F is an isomorphism. So let's prove this. So first to prove that F is injective. Why? Because we know that we have an embedding from the local ring of the base curve into the local ring of the curve C. Okay, but we know that D is smooth, and hence the local ring is a discrete valuation ring. But now the whole thing proceeds in the ring, in the field of fractions of say the base curve D. But you see the DVR, there are no rings between the DVR and its field of fractions. no intermediate rings. Between OD and the field of fractions. So we conclude that it's an equality. Okay, our morphism F induces an isomorphism of local ring. Okay, but then we can apply our old lemma by the first curves lemma. F is injective because the local rings coincide and the maximal ideals also coincide, and there we are. Okay, and well, essentially we are done. Maybe I can only mention that F clearly is a homeomorphism. In the Zariski topology. Because the image and pre-image of any finite set is also finite. Okay, there was so proved this lemma as well, and I hope the next time will be much more interesting because we'll just use those preparational results to prove something substantial about curves. Okay, so thank you. And are there any questions?
Да, может вот по лемме вопрос?
Yes.
Мы, то есть изначально, в принципе, у функции могли быть полюса какие-то, правильно? Но мы доказали, что полюсов нет.
And which lemma are we discussing? The last one?
Вот это. Вот это.
Yes.
Ну, то есть вот
Yes.
в условии там сказано, что f — это бирациональный морфизм. То есть, в принципе, полюса могут быть.
No. It's a regular morphism which is birational. Otherwise, I would say that it's a rational morphism. Maybe I should clarify this point. Sorry. F is regular and birational. So if
хорошо.
I allowed both, I would say that it's a rational morphism. Otherwise, we only consider regular morphisms, and birational means that it's an isomorphism on the field of fraction.
Понятно. Спасибо.
Sorry, yes, sorry about this confusion. So if there are no more questions, let me save the notes and stop the recording.